1998, two teams of astronomers made the same mistake. They were hunting for something completely different. Both groups, one led by Saul Perlmutter at Lawrence Berkeley National Laboratory, the other by Brian Schmidt in Australia with Adam Rees leading the analysis, were trying to measure how quickly the universe was slowing down. That was the question everyone wanted answered. Not whether the universe was slowing. That was assumed. The only mystery was by how much. You see, gravity pulls things together. Always has. Always will. So after the Big Bang flung everything outward, gravity should have been working like a cosmic brake pedal, gradually decelerating the expansion. The universe should have been winding down, like a ball thrown into the air that inevitably falls back to Earth. Both teams were using exploding stars to clock the deceleration, type Ia supernovae. Thermonuclear explosions of white dwarf stars are remarkably consistent in their brightness. They all detonate at roughly the same mass, so they all shine with roughly the same luminosity. This makes them perfect cosmic mile markers. If you know how bright something actually is, and you measure how bright it appears, you can calculate how far away it is. The astronomers found their distant supernovae. They measured their brightness. They did the calculations. And the numbers came out wrong. Not just a little wrong. Fundamentally, catastrophically, reality redefining wrong. The distant supernovae were dimmer than they should have been, which meant they were farther away than expected, which meant that instead of slowing down, the expansion of the universe was speeding up. Both teams checked their data. They checked it again. They looked for errors in their instruments, mistakes in their calculations, dust that might be dimming the light. They found nothing. The conclusion was inescapable. Something was pushing the universe apart. Something invisible. Something that filled all of space. Something that was overpowering the combined gravitational pull of every galaxy, every star, every atom in existence. They called it dark energy. And for 27 years, we've been trying to figure out what it is. Now, new data suggests we might have gotten it wrong from the beginning. Dark energy may not be constant at all. It might be changing, evolving over cosmic time in ways our models never predicted. Should we be afraid? That depends on what afraid means when you're talking about the fate of everything that exists. To understand why the latest discoveries are shaking cosmology to its foundations, we need to understand what we thought we knew. When Perlmutter, Schmidt, and Rees announced their findings, a discovery that would earn them the 2011 Nobel Prize in Physics, they had upended a century of assumptions. But they'd also, almost accidentally, vindicated Albert Einstein's most regretted decision. In 1917, Einstein had just completed his masterwork, the general theory of relativity. His equations described how matter and energy curve spacetime, and how that curvature tells matter how to move. It was brilliant, it was revolutionary, and it had a problem. When Einstein applied his equations to the universe as a whole, they predicted that the cosmos couldn't sit still. Space itself would either expand or contract. There was no stable middle ground. This troubled Einstein deeply. In 1917, everyone believed the universe was static and eternal. The stars hung fixed in their positions. The cosmos simply was, unchanging across the eons. A dynamic, evolving universe seemed philosophically absurd. So Einstein did something that would haunt him for the rest of his life. He added a term to his equations, a cosmological constant, represented by the Greek letter lambda, that would counteract gravity and hold the universe in perfect equilibrium. It was elegant mathematically, even if there was no physical justification for it. Then, in 1929, Edwin Hubble made his observations of distant galaxies and found they were all moving away from us. The farther a galaxy, the faster it receded. The universe wasn't static at all. It was expanding. Einstein reportedly called the cosmological constant his greatest blunder and removed it from his equations. He had let his philosophical preferences override what his mathematics was telling him. If he had trusted his original equations, he could have predicted the expanding universe before Hubble discovered it. For nearly 70 years, the cosmological constant gathered dust in the margins of physics textbooks. Then 1998 happened. When the supernova teams found the universe accelerating, physicists realized with a shock that Einstein's blunder might have been brilliant after all. The cosmological constant could explain everything. If empty space itself contains a tiny amount of energy, what we now call vacuum energy or dark energy, that energy would push space apart. And because this energy is a property of space itself, it wouldn't dilute as the universe expands. As more space comes into existence, more dark energy appears with it. This was simultaneously reassuring and deeply unsettling. Reassuring because it fit neatly into Einstein's framework. The cosmological constant was already there in the equations, just waiting to be given a non-zero value. We didn't need exotic new physics, just a small adjustment to a term Einstein had invented a century earlier. Unsettling because we have absolutely no idea why space should have this energy. Quantum mechanics predicts that empty space should be seething with activity, virtual particles flickering in and out of existence, quantum fields fluctuating at every point. This vacuum energy should contribute to the cosmological constant. When physicists calculate how much energy the quantum vacuum should contain, they get a number. That number is wrong by a factor of 10 to the power of 120. Let that sink in. We're not talking about being off by a factor of 2 or 10 or even a million. The theoretical prediction exceeds the observed value by 120 orders of magnitude, a 1 followed by 120 zeros. This has been called the worst theoretical prediction in the history of physics. If the vacuum energy were actually as large as quantum field theory predicts, the universe would have torn itself apart in the first fraction of a second after the Big Bang. No stars, no galaxies, no planets, no us. The fact that we exist at all means that something, we don't know what, is cancelling out almost all of that vacuum energy, leaving behind just a tiny residue that's now accelerating the expansion. Why? How? What mechanism could possibly fine-tune the cosmological constant to 1 part in 10 to the 120th power? Nobody knows. For a quarter century, cosmologists have been treating this mystery the way you might treat a strange noise in your car that doesn't seem to affect the driving. They noted it, worried about it occasionally, and then carried on with the working assumption that the cosmological constant is just that, a constant, a fixed amount of energy per cubic meter of space, unchanging throughout cosmic history. This assumption is built into what physicists call the lambda CDM model, lambda for the cosmological constant, CDM for cold dark matter. It's the standard model of cosmology, describing a universe that's about 68% dark energy, 27% dark matter, and 5% ordinary matter. It has only 6 free parameters, and it explains an enormous amount of observational data with remarkable precision. Lambda CDM has been the bedrock of modern cosmology, and now cracks are appearing in that bedrock. The trouble started with DESI. The Dark Energy Spectroscopic Instrument sits atop Kitt Peak in Arizona's Sonoran Desert, attached to the Nicholas U. Mile 4-meter telescope. It's an extraordinary piece of engineering. 5,000 robotic fiber optic cables, each thinner than a human hair, can automatically swivel to point at 5,000 different celestial targets simultaneously. On a good night, DESI can record the positions and velocities of nearly 200,000 galaxies. Previous surveys that relied on manually positioning optical fibers could never have dreamed of such speed. DESI's mission is to create the largest 3-dimensional map of the universe ever made. Not just where galaxies are, but how far away they are and how fast they're moving. By charting the positions of millions of galaxies and quasars, intensely bright objects powered by supermassive black holes, DESI can track how the universe has expanded over the past 11 billion years. The key to this measurement is something called baryon acoustic oscillations. In the first 400,000 years after the Big Bang, the universe was a hot, dense plasma of protons, electrons, and photons. Sound waves rippled through this primordial soup, created by the competition between gravity pulling matter inward and radiation pressure pushing it outward. When the universe cooled enough for atoms to form, these sound waves froze in place, leaving behind a subtle pattern in how matter is distributed. Think of it like dropping a pebble in a pond. The ripple expands outward, and if you could freeze the water at that moment, you'd see a ring of slightly elevated water at a specific distance from where the pebble landed. Now imagine dropping billions of pebbles simultaneously. You'd get overlapping rings, creating a complex pattern, but with a characteristic spacing. That characteristic spacing, about 490 million light-years in today's universe, shows up as a preference for galaxies to be separated by that distance. It's subtle, only detectable statistically by mapping enormous numbers of galaxies, but it's there. And crucially, we know from physics exactly how big this standard ruler was when it formed by measuring how large the baryon acoustic oscillation scale appears at different distances, different epochs in cosmic history. Astronomers can track how the universe has been expanding. If dark energy is a constant, the expansion should follow a predictable pattern. Any deviation from that pattern would mean something is wrong with our model. In April 2024, DESI released its first results. The collaboration had mapped nearly 6 million galaxies and quasars, constructing a 3-dimensional atlas of cosmic structure spanning 11 billion years. On its own, DESI's data was consistent with the standard model. Lambda CDM still worked, but when DESI's measurements were combined with other datasets, observations of the cosmic microwave background radiation, studies of how light from distant galaxies is bent by gravity, catalogues of type IR supernovae, something strange emerged. The data preferred a model where dark energy is not constant. In March, 2025, DESI released its second round of results based on 3 years of observations and nearly 15 million galaxies and quasars. The hints had grown stronger. Different combinations of DESI data with other observations gave statistical significances ranging from 2.8 sigma to 4.2 sigma, approaching the 5 sigma threshold that physicists traditionally require to claim a discovery. We're guided by Occam's razor, and the simplest explanation for what we see is shifting, said Will Percival, co-spokesperson for DESI and a professor at the University of Waterloo. It's looking more and more like we may need to modify our standard model of cosmology to make these different datasets make sense together. An evolving dark energy seems promising. Willem Elbers, a postdoctoral researcher at Durham University who co-chairs DESI's Cosmological Parameter Estimation Working Group, put it more starkly. For a couple of decades, we've had this standard model of cosmology that is really impressive. As our data are getting more and more precise, we're finding potential cracks in the model and realizing we may need something new to explain all the results together. What does evolving dark energy mean? It means that the density of dark energy, the amount of energy in each cubic meter of space, may be changing over time. Specifically, the data suggests that dark energy was stronger in the past and is weakening now. If this is confirmed, it would be one of the most significant discoveries in the history of cosmology. The implications are staggering. For 27 years, cosmologists have been assuming dark energy is a cosmological constant. Einstein's lambda, a fixed property of spacetime itself. This assumption leads to a specific prediction about the universe's future: eternal acceleration. Galaxies beyond our local group will recede faster and faster, eventually crossing the cosmic horizon and becoming forever unreachable. Stars will burn out. Black holes will slowly evaporate through Hawking radiation. The universe will expand and cool until, after unimaginably vast stretches of time, it reaches maximum entropy, a state of perfect uniformity where nothing can happen because there are no energy gradients left to drive any process. This is the heat death scenario, also called the Big Freeze. It's bleak, but it's the future most cosmologists have accepted as likely. But if dark energy is changing, all bets are off. The key parameter physicists use to characterize dark energy is called the equation of state parameter, usually denoted by the letter W. It's the ratio of dark energy's pressure to its energy density. For a cosmological constant, W equals exactly -1. This value has deep significance. It means that as space expands, the dark energy density stays exactly the same. New dark energy appears to fill the new space. If W is greater than -1, but less than -1/3, you have what's called quintessence, a dynamic form of dark energy that evolves over time and gradually dilutes as the universe expands. In such a universe, dark energy would eventually become negligible, and the future might look very different from the heat death scenario. But if W is less than -1, you have something far more troubling: phantom energy. Phantom energy doesn't dilute as the universe expands, it grows. The density of dark energy increases over time, and its repulsive effect becomes ever more powerful. Eventually, this runaway acceleration would overwhelm every other force in the universe. First, galaxy clusters would be torn apart, their constituent galaxies flying away from each other at speeds no gravity could overcome, then galaxies themselves would dissolve, their stars scattered into the void. Solar systems would disintegrate, planets ripped from their orbits around their parent stars. But phantom energy wouldn't stop there. As the expansion rate approaches infinity, the fabric of space itself would stretch faster than the forces holding matter together can withstand. Planets would be torn apart, then stars, then atoms. Electrons would be ripped from their nuclei. Protons and neutrons would be shredded into quarks. In the final moments, approximately 1/10,000th of a femtosecond before the end, even the quarks would be ripped apart. This is the Big Rip scenario, proposed in 2003 by physicist Robert Caldwell and his colleagues. If phantom energy is real, the universe would not fade gradually into eternal cold darkness. It would be torn to pieces in a cosmic cataclysm. Current observations, including the DESI results, don't clearly favor phantom energy. The data is consistent with the W being close to -1, possibly slightly greater, possibly slightly less. The uncertainties are still too large to know for sure. But here's what makes the recent findings so provocative. The data suggests that dark energy may have been stronger in the past than it is now. If true, this means dark energy has been weakening over cosmic time. At first glance, this seems reassuring. A weakening dark energy won't tear the universe apart, but the implications cut deeper than the Big Rip. In June 2025, a research team from Yonsei University in South Korea published a paper in Monthly Notices of the Royal Astronomical Society that sent shockwaves through the cosmological community. Lead researcher Professor Youngwook Lee and his colleagues had been studying a subtle but potentially crucial bias in how we use Type Ia supernovae as distance indicators. The brightness of these stellar explosions isn't perfectly uniform. It depends, among other things, on the age of the stellar population that produced the white dwarf progenitor. Older stellar populations produce slightly dimmer supernovae. This might seem like a minor technical detail, but its implications are profound. When the researchers corrected for this age bias and reanalyzed the cosmological data, they found something nobody expected. The universe may have already stopped accelerating. Our study shows that the universe has already entered a phase of decelerated expansion at the present epoch, Professor Lee announced, and that dark energy evolves with time much more rapidly than previously thought. If true, this would mark a major paradigm shift in cosmology since the discovery of dark energy 27 years ago. The standard DESI analysis, which combined uncorrected supernova data with baryon acoustic oscillation measurements, concluded that while the universe would decelerate in the future, it is still accelerating at present. But the Yonsei team's age bias correction paints a different picture. The transition from acceleration to deceleration has already happened. We would be living in a decelerating universe right now without knowing it. This remains controversial. Other researchers have challenged the magnitude of the age bias correction, and independent teams are working to replicate the analysis using different methods. But the fact that such a conclusion is even on the table shows how unsettled the field has become. And there's another puzzle complicating everything: the Hubble tension. The Hubble constant is the number that tells us how fast the universe is expanding right now. It's expressed in kilometers per second per megaparsec. Basically, for every megaparsec of distance, about 3.3 million light-years, galaxies are receding from us at a certain velocity due to cosmic expansion. We can measure the Hubble constant in two completely different ways. The first method uses the late universe, observations of stars and galaxies relatively close to us, cosmologically speaking, by building a distance ladder that chains together various standard candles from nearby Cepheid variable stars to distant type Ia supernova. Astronomers can directly measure how fast space is expanding today. These measurements converge on a value around 73 kilometers per second per megaparsec. The second method uses the early universe, observations of the cosmic microwave background, the afterglow of the Big Bang. By studying the detailed patterns in this ancient light and using our theoretical model of how the universe evolved, cosmologists can predict what the expansion rate should be today. These calculations give a value around 67 kilometers per second per megaparsec. The difference between 73 and 67 might not sound like much, but given the precision of modern measurements, the discrepancy is now statistically significant at more than 5 sigma, well past the threshold for claiming a real effect. Either there's a systematic error in one of the measurement methods that nobody has found despite years of searching, or there's something fundamental wrong with our model of how the universe works. The Hubble tension tells us something is wrong, but it does not precisely point out what, says Adam Rees, who shared the Nobel Prize for discovering cosmic acceleration and has been at the center of the tension debate. Nature is making us work harder to figure out what is going on and why. Recent work has only deepened the mystery. A January 2025 analysis led by Dan Skolnick of Duke University found that the Coma cluster of galaxies, one of the most massive structures in our cosmic neighborhood, is 38 million light-years, closer than it should be according to the standard model. Skolnick's verdict: the Hubble tension is now a Hubble crisis. Could evolving dark energy resolve the Hubble tension? Perhaps. If dark energy behaved differently in the early universe than it does today, that could change the predictions derived from the cosmic microwave background, potentially bringing them into line with the late universe measurements. But we don't yet have a consistent model that explains all the data. Every proposed solution to the Hubble tension seems to create problems elsewhere. As Lloyd Knox, an early universe cosmologist at the University of California, Davis, put it, the lambda CDM model has been amazingly successful. If there's a major overhaul of the model, it's hard to see how it wouldn't look like a conspiracy. Somehow, this wrong model got it all right. The universe is telling us something. We just don't know what yet. There's a deeper question lurking beneath all this technical debate. Why does dark energy exist at all? The cosmological constant problem, that factor of 10 to the 120th discrepancy between theoretical prediction and observation, has been called physics' most embarrassing problem. And it's not just embarrassing, it's existentially strange. Quantum field theory, our best description of the subatomic world, tells us that empty space should be boiling with energy. Every quantum field, and there are many, one for each type of particle, contributes to the vacuum energy. Add them all up, and you get an absurdly large number, Yet the observed cosmological constant is almost, but not quite, zero. If dark energy is a cosmological constant, it has been considered a dead end, says Mustafa Ishaq Boushaki, a theoretical astrophysicist at the University of Texas at Dallas and co-chair of the DESI working group that interprets cosmological data. The difference between theoretical calculations and measurements was known in the field as the most embarrassing difference that we can't explain. Some physicists have proposed that the small value of the cosmological constant is a selection effect. According to this view, the universe might be part of a vast multiverse with many different regions, each with different values of the cosmological constant. In most of those regions, the constant is huge, space expands violently, and no structures can form. No galaxies, no stars, no planets, no observers. We find ourselves in a region with a small cosmological constant because that's the only kind of region where observers like us can exist. This reasoning, advocated by physicist Steven Weinberg in the 1980s, successfully predicted that the cosmological constant should be small but non-zero before it was measured. Some see this as profound evidence for the multiverse. Others see it as a retreat from science into unfalsifiable speculation. But if dark energy isn't a cosmological constant, if it's changing over time, then the multiverse argument loses much of its force. A dynamical dark energy implies there's actual physics we don't understand. New fields or forces that are evolving over cosmic history. That's not a dead end. That's a doorway. If it is true that dark energy evolves with time, this would be one of the most significant discoveries in cosmology in a generation, says Paul Shah, a researcher at University College London who works on supernova observations. It implies something we don't yet understand is causing the change. The next few years will be critical. DESI will continue collecting data through 2026, aiming to map over 50 million galaxies and quasars. If the hints of evolving dark energy persist and strengthen, they could cross the 5 sigma threshold required for a genuine discovery. Meanwhile, other experiments will provide independent checks. The Vera C. Rubin Observatory in Chile began scientific operations in 2025. Its 8-meter telescope will survey the entire southern sky repeatedly, discovering thousands of Type I supernovae and enabling unprecedented measurements of cosmic expansion history. NASA's Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will extend the supernova search far deeper into space and time, probing epochs when dark energy's influence was just beginning to dominate. The European Space Agency's Euclid satellite, launched in 2023, is mapping the distribution of galaxies and dark matter across 10 billion years of cosmic history. Its first cosmological results are expected soon. Each of these instruments brings different strengths and different systematic uncertainties. If they all converge on the same conclusion, that dark energy is evolving, the case will be overwhelming. But if the signals diverge, if different experiments give different answers, then we're back to square one, looking for subtle errors and hidden biases in our measurements. Science is slow. Certainty is hard to come by. And the universe doesn't care whether we understand it or not. So, should we be afraid? The honest answer is, we don't know enough to know what we should be afraid of. If dark energy is weakening, the Big Rip is probably off the table. the universe won't be torn apart in a cosmic apocalypse, but a weakening dark energy could mean that the expansion slows, possibly even reverses. If dark energy fades entirely, gravity could eventually regain the upper hand, pulling everything back together in a big crunch, the Big Bang playing in reverse. Or dark energy might stabilize at some new value, leaving us with an eternally expanding universe that ends in heat death, just at a different rate than we thought. Or our measurements might be wrong, our models incomplete, our understanding of the universe so fundamentally flawed that any prediction about the ultimate fate of the cosmos is premature. There's a strange comfort in that last possibility. It means the story isn't over. The universe still has secrets to reveal. In 1990, at the height of efforts to measure the deceleration of the universe, cosmologist Mike Turner was asked what value the deceleration parameter might turn out to have. He replied that the only cosmological parameter he was sure was precisely zero was the cosmological constant. 8 years later, when the supernova teams announced their discovery, Turner coined the term dark energy for the mysterious force causing the acceleration. Science advances through confident predictions that turn out to be completely wrong. In 2024 and 2025, cosmologists were confident that dark energy was constant, a fixed property of spacetime, unchanging across cosmic history. Lambda CDM was the standard model, tested and verified countless times. Now that confidence is wavering. What was most convincing for me is that the evidence is coming from different directions, says Ishak Bouchaki, and it can't be that all these different directions of different data sets conspire to give the same wrong answer. But Jesse Muir, a cosmologist at the University of Cincinnati and member of the Dark Energy Survey team, urges caution. I'm not going to hold a funeral for the standard cosmological model. I'm cautiously excited. It's something to keep an eye on and prod at, and really try to make sure we understand. Joshua Freeman, a cosmologist at the University of Chicago, who helped found the Dark Energy Survey, remembers previous cosmological anomalies that disappeared with more data. My reaction to this is to be intrigued, he says, but until the errors get smaller, I'm not going to write my Nobel acceptance speech. The scientific community has been burned before by signals that seemed significant and then faded away. In particle physics, they call it the look elsewhere effect. When you examine enough data in enough ways, you'll occasionally find patterns that look meaningful but are actually statistical flukes. But this time feels different to many researchers. The hints are coming from multiple independent lines of evidence: baryon acoustic oscillations, supernovae, the cosmic microwave background, gravitational lensing. For all of these to conspire to give the same false signal would require an extraordinary coincidence. If the evidence continues to grow, and it is likely to, then this will be huge for cosmology and all of physics, says Ishak Bouchaki. I've worked on the question of cosmic acceleration for 25 years, and my perspective is, this is what we've been waiting for. There's a peculiar irony in our situation. Dark energy makes up about 68% of the total energy content of the universe. It's the dominant ingredient in the cosmic recipe, far outweighing all the stars and galaxies and planets and people combined. And yet it remains completely invisible, completely intangible, completely mysterious, We don't know what it is. We don't know why it exists. We don't know if it's constant or changing. We don't know if our best theory of gravity, general relativity, is even the right framework for understanding it. After more than a quarter century of study, after Nobel Prizes and billion-dollar experiments, and the combined efforts of thousands of brilliant scientists around the world, dark energy remains exactly what its name implies. Dark, hidden, unknown. And now, we're getting hints that even our working assumptions about it might be wrong. This is either deeply troubling or deeply exciting, depending on your perspective. If you're the kind of person who finds comfort in certainty, who wants the universe to be comprehensible and predictable, then the current state of cosmology is unsettling. We thought we understood the broad outlines of cosmic history, from the Big Bang to the Big Freeze. Now even that story is in question. But if you're the kind of person who finds wonder in mystery, who sees unanswered questions as invitations to explore, then we're living through an extraordinary moment. The universe is more complicated, more surprising, more unknown than we thought. There are discoveries waiting to be made that could transform our understanding of existence itself. Einstein spent the last decades of his life searching for a unified theory that would explain all the forces of nature in a single mathematical framework. He died without finding it. The universe kept its secrets. A century later, we've made enormous progress. We have a standard model of particle physics that describes 3 of the 4 fundamental forces with exquisite precision. We have general relativity, which describes gravity as the curvature of spacetime. We have lambda CDM, which explains the large-scale structure of the universe from the Big Bang to the present day. But we still don't know what dark energy is. We still don't know why the cosmological constant has the absurdly small value it does. We still don't know if our theories are even approximately correct when it comes to the ultimate fate of the cosmos. The DESI results are the latest reminder that the universe is under no obligation to be simple or comprehensible. It does what it does, following rules we haven't fully decoded. Maybe dark energy is a cosmological constant after all, and the current hints of evolution will fade away with more data. Maybe the standard model will survive this challenge as it has survived others. Or maybe we're standing at the threshold of a revolution comparable to the one Einstein initiated a century ago. Maybe the very concepts we use to describe the universe, space, time, energy, gravity, need to be rebuilt from the foundations. Either way, the story isn't over. The observations continue. The theories evolve. The universe unfolds according to its own logic, indifferent to human hopes and fears. Here is what we know for certain. The universe is expanding. This expansion was initially slowing down as gravity pulled on all the matter in the cosmos. Then, sometime around 5 billion years ago, the deceleration stopped. Something began pushing space apart faster than gravity could pull it together. The expansion started accelerating. We call that something dark energy. We don't know what it is. Recent observations suggest that dark energy may not be constant. It may have been stronger in the past and weaker now. If true, this would overturn 27 years of assumptions and open new questions about the universe's fate. We don't know if these observations are correct. The statistical significance is approaching, but hasn't yet reached. the threshold for discovery. More data will tell. We don't know what it means for the future. If dark energy is evolving, the Big Rip becomes less likely, but other scenarios, continued acceleration, eventual deceleration, possible recollapse, remain on the table. We don't know why dark energy exists at all, why its energy density is so absurdly small compared to theoretical predictions, or what this implies about the fundamental nature of reality. We know vastly more than we did a century ago. We know vastly less than we thought we did a decade ago. The universe keeps surprising us, and perhaps that's the most important lesson of all. For a few decades there, cosmologists thought they had it figured out. Lambda CDM worked brilliantly. The measurements kept getting more precise, and they kept confirming the theory. Dark energy was a constant. The universe would expand forever, and the details were just a matter of refinement. Now that certainty is crumbling, not catastrophically. Lambda CDM is still a good approximation, but visibly, the cracks are appearing. Something unexpected is happening. This is not a failure of science. This is science working exactly as it should. Our theories are provisional, our models approximate, our understanding always incomplete. When the data challenges our assumptions, we don't cling to our assumptions. We question them. We look for better theories. We keep exploring. The universe doesn't owe us simplicity. It doesn't owe us comprehensibility. It doesn't owe us answers that fit neatly into our mathematical frameworks. And yet, somehow, we keep making progress. Slowly, painstakingly, one observation at a time. We're learning how the cosmos works. We're mapping its history, charting its expansion, probing its deepest mysteries. Dark energy is accelerating faster than predicted. Or maybe it's weakening. Or maybe it's doing something we haven't imagined yet. Should we be afraid? Perhaps. The universe is vast and indifferent. It began without us and will continue long after our species is gone. Our planet, our solar system, our galaxy, all of it is a temporary eddy in the cosmic flow, destined to dissolve into the expanding void. But fear is not the only response to cosmic mystery. There's also wonder, curiosity, the profound privilege of being conscious creatures in a universe that permits consciousness, asking questions about our own existence, using mathematics and telescopes and silicon chips to probe the nature of reality. We are matter that has learned to understand itself. Atoms contemplating atoms. Stardust wondering about stars. Dark energy may be evolving. The universe may be more complex than we thought. The future may be more uncertain than our models predicted, but we're still here, still observing, still thinking, still reaching for understanding. That's not nothing. In the grand scheme of cosmic time, it might even be something remarkable. Behind every cosmic measurement, there are human beings. Consider Saul Perlmutter. In 1988, he proposed the supernova Cosmology project with the goal of measuring how much the expansion of the universe was slowing down. He was a young physicist, fresh from his PhD at Berkeley, convinced that type Ia supernovae could be used as precision distance indicators. For a decade, he and his team developed new techniques for finding and measuring distant supernovae. It wasn't glamorous work. Hours at the telescope, waiting for clear weather. Painstaking analysis of faint light from the edge of the observable universe. False starts and dead ends, and endless technical challenges. By 1997, after nearly a decade of effort, the data was starting to come together. Perlmutter expected to find a decelerating universe. That was what everyone expected. The only question was how fast the deceleration was happening. Then the data spoke. In a way, Perlmutter later recalled, the result was so strange that I think we felt almost an intellectual comfort, realizing that we were in one of those moments when you learn something new about the world. The universe wasn't slowing down. It was speeding up. On the other side of the world, Brian Schmidt had formed a rival team, the High Z Supernova Search Team, with Adam Rees leading the data analysis. They used similar techniques but different instruments, different analysis pipelines, different scientists. The two groups were competitors, racing to publish first. And they found the same thing when two independent teams, using different methods, find the same unexpected result. It's much harder to dismiss as error. The accelerating universe wasn't a fluke. It was real. Schmidt remembers the moment of realization. I was really terrified when we got the answer, he said. I thought we had made a mistake. They checked everything. Dust absorption, calibration errors, selection biases. They couldn't make the result go away. In January 1998, both teams presented their findings to the scientific world. The reaction was a mixture of shock, excitement, and skepticism. Some cosmologists immediately recognized the significance. Others demanded more evidence, convinced that such a radical result must be wrong. But the evidence held up. Over the following years, other observations confirmed the accelerating expansion. The cosmic microwave background measurements from the WMAP satellite were consistent with dark energy. Baryon acoustic oscillation studies found the same. Gravitational lensing surveys agreed. In 2011, Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics for the discovery of the accelerating expansion of the universe through observations of distant supernovae. Now, a generation later, the story continues. The scientists working on DESI are the intellectual heirs of those 1990s supernova hunters. Many of them were graduate students or postdocs when dark energy was discovered. They've spent their careers refining the measurements, probing the details, searching for any sign that the standard model might need revision. Mustafa Ishak Bushaki has worked on cosmic acceleration for 25 years. He's seen the field transform from a wild frontier to an established science, from rough estimates to precision cosmology. Now, as co-chair of the DESI working group that interprets the data, he's watching the possibility of another revolution emerge. The standard cosmological model is incredibly successful, he acknowledges, but science progresses when we find places where the models don't quite work. Stephanie Juneau, an astronomer at NSF's NOAA lab and a DESI data team member, remembers what was expected when the experiment began. When the experiment was starting, the assumption was that we would just obtain the highest precision measurement, confirming the constant. It was actually a huge surprise that we found some hint of deviation. Will Percival, co-spokesperson for DESI and a professor at the University of Waterloo, frames the findings carefully. The data alone doesn't prove anything, but combined with other measurements, it suggests something new. We're guided by Occam's razor, Percival says, And the simplest explanation for what we see is shifting. This is how science works in practice. Not sudden eureka moments, but gradual accumulation of evidence, careful statements hedged with uncertainties. Awareness that today's revolutionary hint could be tomorrow's statistical fluctuation. The scientists aren't claiming to have overthrown lambda CDM. They're not announcing that dark energy is definitely evolving. They're presenting data that hints at something unexpected, acknowledging the limitations and calling for more observations. That's not dramatic. That's not headline grabbing, but it's honest. Let me tell you about the telescopes. DESI sits atop Kitt Peak at an elevation of 6,800 feet in the Sonoran Desert of Arizona. The site was chosen for its dark skies, its clear weather, its distance from city lights. Indigenous peoples have considered this mountain sacred for centuries. The Tohono O'odham Nation calls it Yolkum Duag. The telescope itself is a 4-meter mirror, built in 1973 and named after Nicholas Mayle, a pioneering American astronomer who spent decades measuring the speeds and distances of galaxies. For much of its life, the Mayle telescope was used for traditional astronomical surveys, cataloguing stars, studying nebulae, observing planets. Then, DESI arrived. The instrument is a marvel of precision engineering. Those 5,000 robotic fiber positioners, each one capable of independently targeting a celestial object, can reconfigure themselves in under 2 minutes. That means DESI can observe 5,000 galaxies or quasars at once, wait for the light to accumulate, then swivel to 5,000 different targets and repeat. On a single good night, DESI can measure the positions and velocities of nearly 200,000 objects. Over the course of its 5-year survey, it will map over 50 million galaxies and quasars, creating the most detailed 3-dimensional atlas of the cosmos ever assembled. The light DESI captures has traveled for billions of years. Photons that left their source galaxies when the universe was young have crossed the expanding void, dodging through the web of cosmic structure, finally arriving at Kitt Peak to be captured by a mirror and split into spectra. Each spectrum encodes information. The wavelengths of absorption and emission lines reveal what elements the galaxy contains. The shift of those lines toward red wavelengths reveals how fast the galaxy is receding due to cosmic expansion. Combined with the galaxy's position on the sky, this gives its 3-dimensional coordinates in the cosmic web. From these coordinates, cosmologists can measure baryon acoustic oscillations, the standard ruler. They can track how the clustering of galaxies evolves over time. They can constrain the properties of dark energy. It's a remarkable chain of inference. Light from the edge of the observable universe, focused by a mirror, split into colors, analyzed by computer algorithms, converted into constraints on the parameters that govern cosmic evolution. And somewhere in that chain, a hint that dark energy might be changing. The Vera C. Rubin Observatory is another key player. Named after the American astronomer who provided crucial evidence for dark matter in the 1970s, Rubin is located in the Chilean Andes at an altitude of 8,500 feet. Its 8.4-meter mirror is one of the largest ever built for a survey telescope. Its camera, weighing nearly 3 tons, can capture 3.2 billion pixels in a single image. Rubin will survey the entire southern sky repeatedly, taking 2 images of each patch of sky every night. Over a decade, it will observe each region of sky about 1,000 times. This repeated coverage will reveal anything that moves or changes: asteroids, variable stars, supernovae. Those supernovae are crucial for dark energy science. Rubin is expected to discover hundreds of thousands of Type Ia supernovae over its operational lifetime. Each one is a potential standard candle, a data point for measuring the expansion history of the universe. If DESI's hints of evolving dark energy are real, Rubin's supernova sample will provide independent confirmation. If they're not, Rubin will help identify where the discrepancy comes from. The first images from Rubin were released in June 2025. The scientific surveys are now underway. A decade from now, we'll have a treasure trove of data that will transform our understanding of the dynamic universe. Meanwhile, in space, Euclid is mapping the cosmic structure. Launched by the European Space Agency in 2023, Euclid orbits the Sun at the second Lagrange point, about 1.5 million kilometers from Earth. From this vantage point, far from Earth's atmosphere and thermal fluctuations, it can observe with unprecedented stability. Euclid carries two instruments: a visible light camera and a near-infrared spectrometer. Together, they're mapping billions of galaxies across 10 billion years of cosmic history. The primary goal is to measure weak gravitational lensing, the subtle distortion of galaxy shapes caused by the gravitational influence of intervening matter. By analyzing these distortions statistically, Euclid can map the distribution of dark matter throughout the universe and track how cosmic structure has grown over time. This provides another independent constraint on dark energy. If dark energy affects the growth of structure, Euclid will see it. The mission's first cosmological results are expected in 2026, and they'll provide a crucial cross-check on the DESI findings. And then there's Roman, NASA's Nancy Grace Roman Space Telescope, named after NASA's first chief astronomer, is scheduled to launch in 2027. Its 2.4-meter mirror, the same size as Hubble's, will be equipped with instruments designed specifically for dark energy science. Roman will survey large areas of the sky at infrared wavelengths, discovering distant Type Ia supernovae that are invisible to ground-based telescopes. It will measure baryon, acoustic oscillations, and gravitational lensing with precision that surpasses anything we have today. By the early 2030s, Roman's data will be combined with DESI, Rubin, and Euclid. If dark energy is evolving, we'll know. If it's not, we'll have the most precise confirmation of lambda CDM ever achieved. Either way, we'll have learned something profound about the nature of the cosmos. There's a peculiar tension in modern cosmology between the precision of the measurements and the depth of our ignorance. We know the Hubble constant to within a few percent. We know the age of the universe to within a few 100 million years. We know the composition of the cosmos: 68% dark energy, 27% dark matter, 5% ordinary matter, with remarkable accuracy. And yet, we don't know what dark energy is. We don't know what dark matter is. We don't know why the cosmological constant has the value it does. We don't know how to reconcile quantum mechanics with gravity. We don't know what happened at the very beginning or what will happen at the very end. We have an exquisitely detailed map of our ignorance. This is frustrating if you expect science to provide complete answers, but it's exhilarating if you see science as a journey, with each answer opening new questions, each discovery revealing new mysteries. Dark energy might be evolving. If it is, we'll need new physics to explain it. That new physics might connect to other mysteries. The nature of dark matter, the origin of the universe's structure, the unification of fundamental forces. Or dark energy might be constant after all, and the DESI hints might fade away with more data. In that case, we'll have confirmed the standard model once again, and we'll look for cracks elsewhere. Either outcome advances knowledge. Either outcome is a victory for the scientific enterprise. Cosmologists can predict what will happen to the universe on timescales of billions or trillions of years, assuming our current theories are correct. But our theories might be wrong. Almost certainly, they're incomplete. 100 years ago, Einstein had just published general relativity. Quantum mechanics was in its infancy. The existence of other galaxies was still being debated. No one knew the universe was expanding, let alone accelerating. Today, we have a detailed model of cosmic evolution, from the first fraction of a second after the Big Bang to the present day. We can predict the future for billions of years. We've discovered dark matter and dark energy and measured their abundances to percent-level precision. But we still don't know what dark matter is made of. We still don't know why dark energy exists or why it has the value it does. We don't have a quantum theory of gravity that works. We don't know what happened before the Big Bang, or whether before even makes sense in that context. 100 years from now, 1,000 years from now, our descendants might look back at 21st century cosmology the way we look back at Ptolemy's epicycles, clever but fundamentally limited. They might have answers to questions we don't even know how to ask. Or they might still be wrestling with dark energy, still debating whether it's constant or changing, still trying to reconcile quantum mechanics with gravity. We don't know. That's the honest truth. We're making progress. We're learning. Every decade brings new discoveries, new puzzles, new insights. The universe is slowly yielding its secrets. But we're not at the end of physics. We're not even close. Dark energy is a mystery. The DESI results are intriguing. The future of the cosmos is uncertain. And that's okay. That's how science works. That's how understanding grows, not in sudden revelations, but in patient, persistent effort, generation after generation, pushing the boundary of knowledge outward, one experiment at a time. The universe will end, one way or another. That much is certain. Heat death, big rip, big crunch. The details vary, but the conclusion is the same. Nothing lasts forever. Not stars, not galaxies, not the cosmos itself. You might find that terrifying. The utter finitude of existence, the ultimate futility of all striving, the knowledge that everything you love will eventually be erased as though it never was. Or you might find it liberating. If nothing lasts, then nothing needs to last. The meaning isn't in the permanence, it's in the experience. The universe's eventual end doesn't negate the fact that right now it exists, and so do you. We're here, in this moment, contemplating the fate of everything, conscious beings pondering cosmic timescales, stardust wondering about the stars. Dark energy might be changing. The universe might end sooner or later than we thought. The details of our cosmic future might need to be revised, but the essence remains. We exist, we wonder, we seek to understand. That seeking is the point. Not the answers, but the questions. Not the destination, but the journey. The universe is strange, vast, and ultimately unknowable. But we're not looking away. We're building telescopes, mapping galaxies, measuring the faint echoes of the Big Bang. We're refusing to accept ignorance as our permanent condition. Should we be afraid? Perhaps. But we can also be curious and brave and humble. The universe doesn't care about us, but we care about it. We look up at the night sky and ask why. That's enough. That's more than enough. That's everything. The next decade will be decisive. By 2035, we'll have accumulated data from DESI's complete 5-year survey, Rubin's decade-long monitoring of the southern sky, Euclid's all-sky map of cosmic structure, and Raman's deep infrared observations. We'll have measured dark energy's equation of state at multiple epochs across cosmic history, with precision that would have seemed impossible a generation ago. If dark energy is evolving, we'll have mapped out how it changes over time. We'll know whether it's getting stronger, getting weaker, or doing something more complicated. We'll have constraints on theoretical models, quintessence, phantom energy, modified gravity, that will help identify the underlying physics. If dark energy is constant after all, we'll have verified lambda CDM to extraordinary precision. The standard model will be even more firmly established, and the search for cracks will continue elsewhere. Either way, we'll have taken a giant step toward answering one of the deepest questions in science. What is the fate of the universe? But let's be clear about what we won't know. Even with all this data, we won't know what dark energy is. Even if we determine that dark energy is evolving, that it's quintessence rather than a cosmological constant, we won't know what quintessence is made of. We won't know why it exists, why it has the properties it has, why it appeared when it did. We'll have a better phenomenological description, a better equation that fits the data. But the underlying physics will remain mysterious. This isn't a failure. It's the nature of scientific progress. Newton's laws described gravity beautifully without explaining what gravity is. Einstein's general relativity went deeper, explaining gravity as the curvature of spacetime. But general relativity doesn't explain why mass curves spacetime. It just says that it does. Each generation of physicists gets a little closer to fundamental truth. Each generation leaves unsolved problems for the next. Our generation has discovered dark energy and begun to measure its properties. The next generation will probe deeper, perhaps discovering whether it's constant or evolving. The generation after that might finally understand what it is, or not. Some mysteries might take centuries to solve. Some might never be solved at all. There's a temptation, when contemplating the universe, to feel small. 14 billion years of cosmic history, hundreds of billions of galaxies, trillions of stars, distances so vast that light takes millions of years to cross them. Against this backdrop, human civilization is a momentary spark. Our entire recorded history is a rounding error in the cosmic timeline. Our planet is a pale blue dot, barely visible against the vastness of space. And dark energy, the force that will determine the ultimate fate of everything, doesn't know we exist, doesn't care. Will continue doing whatever it does, whether or not anyone is around to observe it. This can feel overwhelming, crushing even. But consider the flip side. Here we are, collections of atoms that have become complex enough to contemplate their own origins. Patterns of matter that have learned to ask questions. Temporary structures that have figured out the age of the universe, the composition of the cosmos, the mechanics of cosmic expansion. We're not separate from the universe. We're part of it. When we study dark energy, the universe is studying itself. That's not nothing. That's remarkable. The story of dark energy begins with Einstein's greatest blunder and continues through a century of observation and theory. It passes through Hubble's discovery of cosmic expansion, through the supernova team's shock at finding acceleration, through decades of refinement and precision measurement. Now, in 2025 and 2026, the story enters a new chapter. The hints from DESI suggest that what we thought we knew might need revision. Dark energy might not be constant. The universe's future might be different from what we imagined. We don't know yet. We need more data. We need more analysis. We need more time. But the fact that we're asking these questions, that we've built the instruments to gather this data, developed the mathematics to analyze it, created the international collaborations to interpret it, that's an achievement worth celebrating. The universe is mysterious. We're solving the mystery. What would it mean for dark energy to be accelerating faster than predicted? It would mean our model is incomplete. It would mean there's physics we don't understand. It would mean the future of the cosmos is more uncertain than we thought. But uncertainty isn't the same as danger. The universe has been doing whatever it's doing for 14 billion years. Whatever dark energy turns out to be, it's been shaping cosmic evolution since the beginning. We're just now learning about it. The discovery that dark energy might be evolving doesn't create new threats. It reveals existing reality. The universe isn't more dangerous because we've learned more about it. It's the same universe it always was. We're just seeing it more clearly. And that clarity is a gift. Think about what it would mean to not know any of this, to look up at the night sky and have no idea that the universe is expanding, that expansion is accelerating, that most of what exists is invisible matter and energy we can't directly detect. For most of human history, that was our situation. We saw the stars and imagined gods and myths and supernatural forces. We had no framework for understanding what we were actually looking at. Now we do. Imperfect, incomplete, constantly being revised, but a framework nonetheless. A way of asking questions and getting answers. A method for distinguishing truth from speculation. Dark energy is real. We've measured it. We're refining our measurements every year. That's not a cause for fear. That's a cause for celebration. Consider for a moment the sheer audacity of what we've accomplished. We are animals, biological organisms that evolved on a small planet orbiting a medium-sized star. Our ancestors spent millions of years focused on immediate survival, finding food, avoiding predators, raising offspring. Nothing in our evolutionary history prepared us for contemplating the fate of the cosmos. And yet here we are. We've built telescopes that capture light from the edge of the observable universe. We've developed mathematics that describes the curvature of spacetime. We've constructed particle accelerators that recreate conditions from the first moments after the Big Bang. We've sent spacecraft beyond the edge of our solar system, carrying golden records with greetings in 55 languages. And now we're measuring whether dark energy, the force that will determine the ultimate fate of everything, is constant or evolving. How remarkable is that? The universe didn't give us this ability. We developed it ourselves through millennia of accumulated knowledge passed from generation to generation, refined and expanded and challenged and improved. Newton built on Galileo. Einstein built on Newton. Modern cosmologists build on Einstein. Each generation stands on the shoulders of giants, seeing a little farther, understanding a little more. Dark energy was discovered in 1998. In just over a quarter century, we've gone from the universe is accelerating and we don't know why, to we're detecting hints that the acceleration might be changing over cosmic time. That's extraordinary progress. That's the scientific enterprise at its best. For now, the answer to the question of what will happen to the universe is, we don't know. We have candidates: heat death, big rip, big crunch, something we haven't imagined yet. We have measurements that favor some scenarios over others. We have theories that make predictions, experiments that test them, data that accumulates, and we have time. Whatever the ultimate fate of the universe, it lies far in the future. Billions of years, trillions, spans so long that human imagination fails to grasp them. In the meantime, we're here, thinking, wondering, building telescopes and training them on the sky, gathering photons that have traveled for billions of years, extracting information about the cosmos, pushing back the boundaries of ignorance. Dark energy is accelerating, faster than predicted. Maybe. Should we be afraid? That depends on what you're afraid of. If you're afraid of uncertainty, then yes, be afraid. The universe is deeply uncertain, and every new discovery reveals new mysteries. If you're afraid of cosmic indifference, then yes, be afraid. The universe doesn't care about us, and dark energy will do what it does regardless of our preferences. But if you can make peace with uncertainty, if you can find wonder rather than terror in the vastness of the unknown, then no, don't be afraid. Be curious. Be humble. Be grateful that we live in an age when these questions can be asked and sometimes answered. The universe is strange. Dark energy is mysterious. The future is unknown, and we're paying attention. That's the human response to the cosmos. Not fear, not despair, curiosity, wonder. The stubborn refusal to stop asking questions. The night sky waits, full of secrets. We're going to uncover them, one photon at a time. The cosmic microwave background is the oldest light in the universe. About 380,000 years after the Big Bang, the cosmos had cooled enough for protons and electrons to combine into neutral hydrogen atoms. Before that moment, photons couldn't travel far without bouncing off free electrons. The universe was opaque, like a fog. But once the electrons were captured into atoms, the photons were released. They've been traveling ever since, gradually cooling and stretching as the universe expanded around them. Today, that primordial light bathes us from every direction. It's been redshifted into microwaves with a temperature of just 2.7 degrees above absolute zero. It's remarkably uniform, almost exactly the same brightness and temperature no matter which direction you look. Almost, not quite. There are tiny fluctuations in the cosmic microwave background, variations of about 1 part in 100,000. These fluctuations are the fossil record of the infant universe. They encode information about the density of matter, the geometry of space, and the physics that governed cosmic evolution. In 2018, the European Space Agency's Planck satellite completed its final analysis of the cosmic microwave background, measuring its fluctuations with unprecedented precision. From these measurements, cosmologists extracted the parameters that describe our universe: how much dark matter, how much dark energy, how fast it's expanding, how old it is. The results painted a picture of a universe that's 13.8 billion years old, dominated by dark energy, with a Hubble constant of 67.4 kilometers per second per megaparsec. But here's the crucial thing. Those numbers depend on assumptions. You can't extract the Hubble constant from the cosmic microwave background directly. You have to plug in a theoretical model, lambda CDM, and use it to evolve the universe forward from that primordial snapshot to the present day. The Hubble constant you get is only as reliable as the model you use. If dark energy has been changing over cosmic history, then lambda CDM isn't quite right, and the numbers extracted from the cosmic microwave background need to be revised. This is why the DESI results are so provocative. They're suggesting that the model we use to interpret our oldest and most precise cosmological data might be systematically biased. Let's talk about what we mean by standard candles and standard rulers. A standard candle is an object with a known intrinsic brightness. If you know how luminous something actually is, and you measure how bright it appears, you can calculate how far away it must be. The dimmer it appears, the farther it is. Type Ia supernovae are the gold standard of standard candles. When a white dwarf star, the dense remnant of a sun-like star that has exhausted its nuclear fuel, accretes matter from a companion star, it can reach a critical mass limit called the Chandrasekhar mass, about 1.4 times the mass of our Sun. At that point, the white dwarf can no longer support itself against gravitational collapse. Carbon and oxygen in its core begin fusing in a runaway thermonuclear reaction. The entire star explodes. Because all white dwarfs explode at roughly the same mass, all type Ia supernovae release roughly the same amount of energy. Their peak brightness varies somewhat, but there's a remarkable relationship. Brighter supernovae fade more slowly. Dimmer ones fade faster. By measuring how quickly a supernova fades, you can correct for its intrinsic variation and standardize all type Ia supernovae to a common luminosity. This is what Perlmutter, Schmidt, and Rees were doing in the 1990s. They found distant type Ia supernovae, measured their apparent brightness and fade rate, calculated how far away they must be, and compared that distance to their redshift, how much their light had been stretched by cosmic expansion. The result shocked everyone. The distant supernovae were too dim. They were farther away than expected for a universe slowing down. The only explanation was that the universe was speeding up. But here's where it gets complicated. Recent work, like that of the Yonsei University team, suggests that type ER supernova brightness might depend not just on the fade rate, but also on the age of the stellar population that produced the white dwarf. Older stars might produce slightly different supernovae than younger ones. If this age bias is real and significant, it could systematically distort the distances we've been measuring. This doesn't mean the discovery of cosmic acceleration was wrong. Multiple independent lines of evidence, baryon acoustic oscillations, gravitational lensing, the integrated Sachs-Wolf effect, all point to accelerating expansion. But it might mean that the precise way dark energy has behaved over cosmic history is different from what we thought. A standard ruler, by contrast, is a feature of known physical size. If you know how big something actually is, and you measure how large it appears, you can calculate its distance. Smaller apparent size means greater distance. Baryon acoustic oscillations provide the cosmic standard ruler. The physics of the early universe, sound waves propagating through the hot plasma before atoms formed, left an imprint of a specific size in how matter is distributed. That size, about 150 megaparsecs today, shows up as a subtle preference for galaxies to be separated by that distance. DESI measures baryon acoustic oscillations at many different redshifts, corresponding to many different epochs in cosmic history. At each epoch, it measures how large the standard ruler appears. By tracking how the apparent size changes with redshift, DESI reconstructs the expansion history of the universe, unlike Type Ia supernovae, which depend on the physics of stellar explosions. Baryon acoustic oscillations depend only on well-understood physics from the early universe. The size of the standard ruler is set by fundamental constants and the composition of the primordial plasma. It's almost immune to the kind of systematic uncertainties that might affect supernova measurements. That's why the DESI results are so compelling. They're finding hints of evolving dark energy using a method that's largely independent of the supernova techniques that first discovered cosmic acceleration. There's another mystery lurking in the data, one that might be connected to dark energy, but might be something else entirely. It's called the S8 tension. C8 is a parameter that describes how clumpy the universe is, how much matter has clustered together into galaxies and galaxy clusters versus how evenly spread out it remains. A higher S8 means more clumping. A lower S8 means a smoother distribution. Just like the Hubble constant, S8 can be measured in two ways. You can calculate what it should be today based on observations of the cosmic microwave background and the lambda CDM model. Or you can measure it directly by studying how light from distant galaxies is bent and distorted by the gravitational influence of intervening matter, a technique called weak gravitational lensing. These two methods give different answers. The cosmic microwave background, filtered through lambda CDM, predicts a higher S8 than what weak lensing surveys measure. Matter seems to be less clustered than the standard model predicts. The S8 tension is less severe than the Hubble tension, about 2 to 3 sigma versus 5 sigma, but it's been persistent. And like the Hubble tension, it could be telling us that lambda CDM is missing something. Could evolving dark energy explain both tensions? Perhaps. If dark energy was stronger in the past, it would have suppressed the growth of cosmic structure, leading to less clumping today, a lower S8. And if the interplay between dark energy and matter was different than lambda CDM assumes, it could also affect the relationship between early universe and late universe measurements of the Hubble constant. But fitting all the data together is extraordinarily difficult. Every proposed modification to lambda CDM seems to fix one problem while creating others. There's no elegant single bullet that explains everything. This is either frustrating or exciting, depending on your temperament. Let's imagine for a moment that the DESI hints are correct. Dark energy really is evolving. It was stronger in the past and is weakening now. What does this mean physically? The cosmological constant, Einstein's lambda, is the simplest possible form of dark energy. It's just a number, a constant energy density that pervades all of space. It has no dynamics, no evolution, no internal structure. It's the universe's most boring possible explanation for why expansion is accelerating. But if dark energy is changing over time, it can't be a cosmological constant. It must be something else. The leading alternative is quintessence. Quintessence is named after the fifth essence of ancient Greek philosophy, the perfect, unchanging substance that was thought to make up the celestial spheres. Ironically, modern quintessence is defined by its ability to change. In technical terms, quintessence is a scalar field, a quantum field that assigns a number to every point in space. Unlike the electromagnetic field, which has both magnitude and direction, a scalar field has only magnitude. The famous Higgs field, which gives particles their mass, is another example of a scalar field. A quintessence field would have energy, and that energy would contribute to dark energy. But unlike a cosmological constant, a quintessence field can evolve. Its energy density can change as the field rolls down its potential. Think of a ball rolling down a hill, gradually losing potential energy. If the DESI data is pointing toward evolving dark energy, quintessence is a natural explanation. The field was at a higher energy level in the early universe, producing stronger dark energy. Over cosmic time, it's been rolling toward lower energy, weakening dark energy's influence. Different quintessence models have different potential energy landscapes, different shapes for the metaphorical hill the field is rolling down. Some predict gradual changes, others predict more dramatic transitions. The precise pattern of how dark energy evolves over time can distinguish between these models. This is exactly what DESI is designed to measure. By charting the expansion history of the universe with exquisite precision, DESI can trace the evolution of dark energy and constrain the shape of the quintessence potential. If the hints hold up, we might not just discover that dark energy is evolving, we might learn what it's made of. But quintessence isn't the only possibility. Modified gravity theories propose that dark energy isn't really a substance at all. Instead, what we interpret as dark energy might actually be a sign that Einstein's general relativity doesn't quite work on the largest cosmic scales. General relativity has been spectacularly successful at describing gravity in our solar system, in binary pulsars, in the gravitational waves from merging black holes. But all these tests involve relatively strong gravitational fields. On the scale of the entire universe, where gravity is extremely weak, we've never directly tested whether general relativity still applies. Could the cosmic acceleration be a clue that gravity itself behaves differently than we thought? In 2026, researchers at the University of Bremen published a paper in the Journal of Cosmology and Astroparticle Physics, proposing a new theory of gravity based on Finsler geometry, a generalization of the geometry that underlies general relativity. They showed that their model could explain cosmic acceleration without invoking any dark energy at all. This is a radical idea. If correct, it would mean that dark energy doesn't exist. that the accelerating expansion we observe is an illusion created by our use of the wrong gravitational theory. Most cosmologists are skeptical. General relativity has survived every test thrown at it, and modifying it in a way that preserves its successes while explaining cosmic acceleration without dark energy is extremely difficult. But the possibility remains on the table. The beauty of cosmological observations is that they can distinguish between these scenarios. Dark energy and modified gravity make subtly different predictions for how cosmic structure grows over time, for how light is bent by gravitational lensing, for the precise pattern of baryon acoustic oscillations. As DESI and other surveys accumulate data, they'll be able to tell us whether we need new substances, new physics, or both. There's one more possibility we need to consider, even though it's the most unsettling of all. What if the universe isn't as uniform as we assume? The entire edifice of modern cosmology rests on something called the cosmological principle, the assumption that, on sufficiently large scales, the universe looks the same in every direction and from every location. No special places, no preferred directions. The cosmos is homogeneous and isotropic. This assumption is supported by observations of the cosmic microwave background, which is remarkably uniform, the same temperature to within a few parts per million in every direction. It's supported by galaxy surveys, which show that on scales larger than a few hundred megaparsecs, the distribution of matter is smooth and featureless. But what if the cosmological principle is only approximately true? What if there are subtle variations in the properties of space from one cosmic region to another? In such a universe, dark energy might not be evolving at all. Instead, we might be living in a slightly unusual region, one where the local expansion rate or the local dark energy density is different from the cosmic average. The Hubble tension might not be tension at all, just the expected difference between local and global measurements in an inhomogeneous cosmos. This possibility is hard to test. By definition, we can only observe the universe from one location. If there are variations on scales larger than our cosmic horizon, we'd have no way to detect them directly. But some researchers are taking this possibility seriously. They're developing statistical techniques to search for anisotropies in the cosmic microwave background, for directional variations in the supernova data, for any hint that the cosmological principle might be breaking down. So far, the universe appears remarkably uniform, but appearances can be deceiving. Where does this leave us? In a state of productive uncertainty. The standard model of cosmology, lambda CDM, has been extraordinarily successful. It explains the cosmic microwave background, the large-scale structure of galaxies, the expansion history of the universe, the abundances of light elements formed in the Big Bang. It does all this with just 6 free parameters. But it also has problems. The Hubble tension, the S8 tension, the absurd fine-tuning required to explain the small value of the cosmological constant, and now the DESI hints that dark energy might be evolving. Something has to give. Either these tensions are systematic errors, subtle mistakes in our measurements, or analyses that will eventually be found and corrected, or they're pointing toward genuinely new physics. The history of science is full of both outcomes. Sometimes anomalies disappear with better data. Sometimes they herald revolutions. The discovery that the universe is accelerating was just such a revolution. A quarter century ago, It overturned everything cosmologists thought they knew about the future of the cosmos. The scientists who made that discovery freely admit they expected to find the opposite. Now, we might be on the verge of another such shift. Dark energy might not be constant. It might be weakening. The universe's future might be different from what we've been imagining for 27 years. Or not. The data isn't conclusive yet. The statistical significance is tantalizing but not definitive. More observations are needed. That's the honest scientific answer. Not certainty, but informed uncertainty. Not knowledge, but the boundary between knowledge and ignorance, constantly shifting as new data comes in. The DESI collaboration will release its next round of results in the coming years. The Vera Rubin Observatory will begin its decade-long survey of the southern sky. The Nancy Grace Roman Space Telescope will launch and turn its instruments toward the distant cosmos. The Euclid satellite will complete its mapping of cosmic structure. Data will accumulate. Theories will be tested. Some will survive. Others will fall. And eventually, perhaps in a few years, perhaps in a few decades, we'll know whether dark energy is constant or evolving. We'll know whether lambda CDM needs to be modified or replaced. We'll know whether we're heading toward heat death, big rip, big crunch, or something else entirely. Or maybe we'll just have better questions. That would be fine too. Science doesn't promise final answers. It promises a process, a way of interrogating reality that gets progressively closer to truth, even if truth itself remains forever just out of reach. Dark energy is real. It's mysterious. It might be changing, and we're going to figure it out. That's not fear. That's not resignation. That's ambition. That's curiosity. That's the human spirit refusing to accept ignorance as permanent. The universe is strange, vast, and indifferent. But we are paying attention. We are asking questions. We are, against all odds, beginning to understand. The night sky looks the same as it always has. The same stars, the same constellations, the same moon. But somewhere out there, in the vast spaces between galaxies, something is pushing everything apart. Something we can't see, can't touch, can't explain. We call it dark energy. We don't know what it is. We're working on it. Let's talk about time. In our everyday experience, time flows forward, relentlessly, at a steady pace. 1 second follows another. The past is fixed. The future is unknown. This seems so obvious that it hardly needs stating. But in cosmology, time is more subtle. The expansion of the universe affects time in ways that challenge our intuitions. Distant galaxies aren't just far away in space. They're also far away in time. When we observe a galaxy 10 billion light years away, we're seeing it as it was 10 billion years ago. The light now reaching our telescopes left that galaxy when the universe was less than 4 billion years old, before our own solar system even existed. This means that cosmological surveys are, in a very real sense, time machines. DESI isn't just mapping the distribution of galaxies in space. It's mapping the evolution of cosmic structure across billions of years. Each slice of redshift corresponds to a different epoch, a different age of the universe. When cosmologists say that dark energy might be evolving, they're saying that the properties of the universe are changing over these vast timescales. The cosmos today is fundamentally different from the cosmos 5 billion years ago, not just in the positions of galaxies, but in the underlying physics that governs expansion. This is mind-bending. We're accustomed to thinking of physical laws as eternal and unchanging. Gravity has always pulled masses together. The speed of light has always been 300,000 kilometers per second. These constants are constant. But dark energy, if it's quintessence rather than a cosmological constant, introduces dynamics into the fabric of spacetime itself. The constant isn't constant anymore. The rules are changing, slowly, over cosmic time. What does this mean for the far future? If dark energy is weakening, then at some point, it might weaken enough for gravity to regain control. The expansion would slow, stop, and potentially reverse. Billions of years from now, perhaps tens or hundreds of billions, the universe could begin contracting. At first, the contraction would be imperceptible. Galaxies would approach each other so slowly that nothing would seem different. But as eons passed, the compression would intensify. The cosmic microwave background would shift from microwaves to infrared, then to visible light, then to ultraviolet. The sky would brighten, temperatures would rise. Eventually, in the final moments before the big crunch, all the matter and energy in the universe would be compressed into a point of infinite density, a singularity, like the one that existed at the Big Bang, but now marking an ending rather than a beginning. Would anything survive such a cataclysm? Almost certainly not. No known physical structure, no galaxy, no star, no planet, no molecule, no atom could withstand the temperatures and densities of a big crunch. Everything we know would be obliterated. But some physicists have speculated that a big crunch might trigger a new Big Bang, a cosmic rebirth, with a new universe emerging from the ashes of the old. This is the cyclic model of cosmology, in which the universe eternally oscillates between expansion and contraction, each cycle erasing all evidence of the previous one. It's a poetic idea, but there are serious problems with it. The second law of thermodynamics says that entropy, the measure of disorder, always increases. Each cycle would inherit more entropy from the previous one, which should change the character of the oscillations over time. Eventually, the cycles would have to stop, unless dark energy or some other mechanism can somehow reset the entropy between cycles. But we have no theory that explains how this could happen. Alternatively, if dark energy is not just weakening, but eventually becomes negative, switches from pushing to pulling, the universe's fate would be even more dramatic. A negative cosmological constant would add to gravity's attractive pull rather than opposing it. Even if the universe had been expanding, a negative dark energy would eventually halt that expansion and drive a contraction regardless of the geometry of space. This scenario is different from a big crunch, caused simply by weakening dark energy. It would happen faster and more violently. The universe wouldn't just gently deflate, it would be pulled inward with increasing force. Some string theory models predict that our universe might exist in a false vacuum, a state that appears stable but is actually metastable, like a ball balanced on a hilltop. If the vacuum were to decay into a lower energy state, the cosmological constant could change abruptly and catastrophically. Such a vacuum decay would spread outward at the speed of light from wherever it started, rewriting the laws of physics as it went. We would have no warning. One moment, the universe would be normal. The next, a bubble of different physics would engulf us, destroying everything inside it. This is probably not something to worry about. There's no observational evidence that our vacuum is unstable. And even if it were, the timescale for decay could be vastly longer than the current age of the universe. But the fact that physics allows such scenarios, that the equations don't forbid them, is a reminder that the universe owes us nothing. Stability is a gift, not a guarantee. What if dark energy isn't changing at all? What if the DESI results are a statistical fluctuation, and 5 years from now, with more data, the anomaly disappears? This is entirely possible. In fact, many cosmologists consider it the most likely outcome. 3 sigma and 4 sigma signals have vanished before. The history of physics is littered with tantalizing hints that led nowhere. If dark energy is indeed a cosmological constant, Einstein's lambda, unchanging across cosmic time, then the heat death scenario remains our most probable future. In this scenario, the expansion continues forever, and the universe gradually cools and empties. Stars exhaust their fuel and fade away. Stellar remnants, white dwarfs, neutron stars, black holes, drift through an ever-expanding void. Galaxies that haven't merged are carried apart, each one becoming a solitary island in an infinite sea of darkness. On a timescale of about 10 trillion years, the last stars will burn out. The universe will enter the degenerate era, when the only remaining structures are dead stellar remnants and stray particles. Then, over unimaginably longer stretches, 10 to the 40th power years, 10 to the 60th power years, even the protons and neutrons that make up atomic nuclei may decay, assuming certain theories of particle physics are correct. The universe would become a thin soup of electrons, positrons, and photons, gradually cooling toward absolute zero. Black holes, the most durable structures in the cosmos, would survive the longest. But even they aren't immortal. Through a quantum process called Hawking radiation, black holes slowly evaporate, emitting particles and shrinking over time. A black hole with the mass of our Sun would take about 10 to the 67th power years to evaporate. A supermassive black hole at the center of a galaxy could last 10 to the 100th power years or longer. But eventually, even the black holes would be gone. After that, in what physicists call the dark era, the universe would be essentially empty, a vast expanse of space at a temperature infinitesimally above absolute zero, with nothing happening forever. This is heat death, maximum entropy, thermodynamic equilibrium, the end of all processes, all structures, all change. It sounds bleak, and in some ways, it is. The heat death of the universe is the ultimate expression of the second law of thermodynamics, the inexorable march toward disorder that governs all physical systems. But there's another way to look at it. The heat death won't happen for an almost inconceivably long time. Even the shortest estimates place it tens of billions of years in the future, the longest stretch to 10 to the 100th power years or beyond. On these timescales, human civilization, indeed intelligent life of any form, has time to evolve, flourish, spread, and perhaps even engineer solutions to problems we can't currently imagine. Maybe intelligence can find ways to extract useful energy even from a low-entropy universe. Maybe consciousness can adapt to exist in forms we've never conceived. Maybe the far future will be richer and stranger than we can possibly predict. Or maybe not. Maybe heat death is truly the end. Either way, we're not there yet. We have billions of years ahead of us. That's time enough for wonders we haven't dreamed of. The universe doesn't care whether we're afraid. It will do what it does regardless of our emotional response. Stars will form and die. Galaxies will collide and merge. The expansion will continue, accelerating, decelerating, or something else entirely, whether or not we ever understand why. But we can choose how to respond to cosmic mystery. We can respond with fear, seeing the vastness and indifference of the universe as a threat to our significance. We can respond with denial, refusing to grapple with truths that make us uncomfortable. Or we can respond with wonder, recognizing that the very capacity to ask these questions, to measure these distances, to contemplate these timescales, is itself a miracle of sorts. Consciousness contemplating its own context. Matter understanding matter. Dark energy is accelerating the expansion of the universe. It might be changing over time. We don't know what it is or why it exists. This is not a failure. This is the frontier. Every unanswered question is an invitation to discovery. Every mystery is an opportunity to learn something new about the nature of existence. The night sky waits, full of secrets. We're going to uncover them. The DESI telescope sits atop a mountain in the Arizona desert, its 5,000 robotic fibers swiveling through the night, gathering light from galaxies billions of years away. Each fiber captures a tiny stream of photons, ancient light that left its source when the universe was young, when dark energy was perhaps behaving differently than it does today. In laboratories around the world, physicists are analyzing this data, running simulations, testing hypotheses. They're comparing DESI's measurements to predictions from lambda CDM, looking for discrepancies, quantifying uncertainties. They're arguing in conference rooms and coffee shops about what the numbers mean. This is science in action, not the heroic narrative of lone geniuses having sudden revelations, but the slow, collaborative work of hundreds of researchers pushing incrementally toward understanding. Most of their papers will be read by a few dozen specialists. Most of their ideas will turn out to be wrong. But somewhere in all that effort, truth is being approached. The hints that dark energy might be evolving could be the first tremors of a scientific earthquake, or they could be noise, statistical fluctuations that will disappear with more data, leaving lambda CDM intact. We won't know for years, maybe a decade, maybe longer. That's frustrating if you want immediate answers. But science has never been about immediate answers. It's about the patient accumulation of evidence, the gradual elimination of possibilities, the slow convergence on truth. The universe took 14 billion years to get here. We can take a few more to figure it out. Meanwhile, the expansion continues. Dark energy, whatever it is, pushes space apart. Galaxies recede, photons stretch. The cosmic horizon shrinks or grows, depending on details we haven't yet measured. And here on Earth, on this tiny planet orbiting an ordinary star in an unremarkable galaxy, creatures made of carbon and water are building instruments to measure the fate of everything. Think about that. We're atoms that have become complex enough to ask questions about other atoms. We're patterns of matter that have learned to study the laws governing all matter. We're temporary structures that have figured out the age of the structures that contain us. The universe produced us, and now we're looking back at it, trying to understand where it came from and where it's going. Dark energy is accelerating faster than predicted. Or maybe it's not. Maybe our predictions were wrong. Maybe our measurements are incomplete. Maybe the truth is stranger than any model we've imagined. Should we be afraid? The universe doesn't care about the answer to that question. It will do what it does. But we can choose our response. We can choose curiosity over fear, wonder over despair, the stubborn insistence on understanding over the comfortable acceptance of ignorance. That choice, that refusal to stop asking questions, is what makes us human. Is what built telescopes and particle accelerators and space probes. Is what discovered that the universe is expanding, that expansion is accelerating, that most of what exists is stuff we can't see or touch, and is what will eventually answer the question that's been driving cosmology for a century. What is the fate of the cosmos? We don't know yet, but we're working on it. And that work, that endless, patient, collaborative effort to understand, is the most remarkable thing the universe has ever produced. The night sky waits. The telescopes are watching. The data is accumulating. Somewhere in those numbers, the answer is hiding. We just have to find it.